Okay, so are there any questions?
No questions at all. It was completely trivial. Okay, I don't know if that's a good sign or a bad sign. Um, let's see. If there are no questions to start, then maybe I can, let me just grab my some more notes here, and I can talk about another topic. Hang on one second. Oh, Wayne Zhao has a question. Perfect. We'll answer Wayne's question while I pull up
Yeah, I have a quick question about when you were describing the photon as a goldstone.
Yes.
Um, we were describing it in terms of one of the one was it, if I understand correctly, it was in terms of one of the one form symmetries that was broken.
Yes.
Uh, um, so if you have both the electric and the magnetic U1s broken, would what would that mean? Would that mean that there will be two photons that are goldstones, or are they coincident somehow?
Well, they won't be spontaneously broken. Maybe that's one thing to say. Um, yeah, I mean they just won't be spontaneously broken. In they're not spontaneously broken by Maxwell, by free Maxwell theory. I mean, generally speaking, one expects the reason it can't just be sorry, what happened to my screen share here? The reason it can't just be so what could be an answer to this question? Well, generally speaking, you would expect that every U1 symmetry that is broken gives rise to a Goldstone boson. And in the higher form sense, that's also true, where the Goldstone bosons get form indices. So spontaneously breaking a one-form U1 global symmetry gives you a photon. Spontaneously breaking a U1 two-form global symmetry would give you a two-form gauge field. And it's hard to reproduce all the features of these global symmetries with a single, with multiple U1s, in part because there are, I didn't tell you about it, but there's a kind of mixed anomaly. So maybe I should use this to segue into that. So let's look at, well, let's write the whole thing. All right, F minus BE squared plus 1 over 2 pi integral of F wedge B magnetic. So this is the action that we discussed for Maxwell theory coupled to electric and magnetic background fields. So and BM are background fields. So this action actually has a very interesting anomaly. Let's see if we can figure it out. So what happens when BE goes to BE plus D, let's call it lambda E? This is a one form. And BM goes to BM plus d lambda m. Now, under this transformation, I also want A to go to A plus B. So what happened? So perhaps people can see, but I will write it anyway. S Maxwell goes to integral of dA plus d lambda e minus b e minus d lambda e all squared plus 1 over 2 pi integral of dA plus d lambda e wedge Bm goes to Bm plus d lambda m. Okay, so this cancels with this. Sorry, this is the change. So the first term has returned to itself. We'd like to separate off the second term here. So this altogether is the old S Maxwell that we had. Now we have some terms. Let's see if we can write them down. We have 1 over 2 pi integral dA d lambda m plus d lambda e bm plus d lambda e d lambda m. So these are our kind of new terms that we should study. And what can we say about them? Can people see any way to simplify these terms? What kind of quantization properties do all these times here, I should say, are wedges. What kind of quantization properties do gauge parameters have? So first of all, that 1 over 2 pi integral dA, this is an integer. And so is integral d lambda e or m over 2 pi. This is also an integer. Okay, so given that, what do you think is going on up here? So this term is 2 pi times integer. Because integral of dA over 2 pi over any 2 cycle is an integer, and integral of d lambda m over 2 pi is an integer. And similarly, this term here is also 2 pi times integer. And we're considering e to the if. So shifting the action by 2 pi integer does nothing. So these terms, although they look non-trivial, they're actually just shifting the action by 2 pi integer, so we don't care about them at all. So what we learned from that is that S Maxwell goes to S Maxwell, which is this bit that we already identified, plus this one term here. This is an anomaly. It's a mixed anomaly between the U1 one form electric and the U1 one form magnetic. Right? Remember what I told you about anomalies. I told you that you're supposed to consider general gauge transformations and ask whether the action is gauge invariant, and if not, what happens? And so here we see that there's this local term. It's a local function of the background field B and the gauge parameter lambda E that parameterizes the difference. And so what that means, so this anomaly is actually, of course, RG invariant. So any theory that you can obtain from the Maxwell theory by RG or interactions or anything like that, continuous deformations, must exhibit this same anomaly. And that's not super easy to do. So in particular, this anomaly tells you something about the two-point function of these currents. And that two-point function is exactly what is there for Maxwell theory. It fixes the two-point function to be the same form. Okay, so that was a very long digression about your question, but hopefully illustrates something interesting.
Maybe I can follow up. So what is, I understand that there's something I don't understand. This is a classical calculation, right? So
anomalies have nothing to do with classical versus quantum. This is just like some way in which some set of examples are discussed. It's just a question. It's just a question about what happens to the action, what happens to the partition function under gauge transformations. Whether we decide to call some of it classical or some of it quantum, this is not even duality invariant.
So why can't we just tell that this is the non-invariance of the action? So there's just no symmetry, no invariance?
Well, yeah. So how does one diagnose whether a symmetry is there? You diagnose that by looking at whether the current is conserved at separated points. And here, what I've told you is this is a local function of the sources. So it means that the mistake in current conservation is only at coincident points. So the current is conserved. So divergence of F is 0, divergence of star F is 0. But in the presence of star F, so what this is telling you is something like d mu F mu nu of X correlation function with star F. Let me even omit rho sigma of Y. That this has got something in it which is like delta 4 of X minus Y. So naively, you think it's not 0, you think it should be 0. And the divergence of the current is 0 at separated points. It's the statement that there is a symmetry. When one says there's a symmetry in quantum field theory, you mean that the current is conserved at separated points. The anomaly is telling you about what's happening at coincident points. Some behavior, some non-conservation that you can't remove at coincident points. And that's what's happening here. We could even try and get the indices right if we want. So I suspect that this is d lambda, and then I'm supposed to have something like epsilon lambda nu rho sigma, like that. And then there's some number here that's pi's, not 0.
But does the classical action have this sort of conserved current?
I'm not sure. I mean, the current we're talking about is F mu nu. So the equation of motion is F mu nu equals divergence equals 0. And there's also the Bianchi identity, which says that d mu star F mu nu equals 0. And these equations hold at separated point. This is the same as when you study any current in quantum field theory. The divergence of that current is 0 at separated points, and then at coincident points there can be interesting corrections like ward identities or anomalies. Yeah, I'm just doing the same thing for currents with more indices.
Are there any other questions? I did remember a question from yesterday, so I wanted to maybe understand better the definition. Yes, sorry.
Go, please.
Yeah, definition of the gauge field for discrete symmetries, right? In terms of holonomies, and so what is, well, you mentioned what it means, the, well, closedness condition, right? So you have to have trivial holonomy, basically, right?
Closed means the holonomy, so
closed
integral over gamma of A equals 1 if gamma is the boundary of something. That means that then you would say that A is closed. So this is a condition on A, that whenever you have a one cycle that's topologically trivial, it's the boundary of some disk or some two manifold, then the holonomy around that one cycle is trivial. That's the condition on A.
Right, and what was the exactness then?
Yeah, okay. So then we'll have to say a little more. So A can shift by not quite the exterior derivative because we're doing something in discrete cohomology. So it will be a kind of well, it will be delta kind of notation. Let's call it eta. So eta here is in the mathematical terminology would be a zero cochain, a zero a zero cochain on M with coefficients in the group G that we're talking about, and this is a differential in the cohomology.
So my understanding was
it's simplest to think about this if you imagine putting a lattice on your manifold. So imagine you want. So it's easiest to talk about discrete gauge fields concretely when you have some triangularization of your manifold. So let's do that. Okay. Then we have 0 cycles, 1 cycles, 2 cycles, etc. And what this kind of eta is it's something that that assigns an element of G to each point in the triangulation. So if you like, that's a gauge transformation. It's something where you do a gauge transformation by an element G at each point in the triangulation. Whereas A is something that assigns a group element to each link. And so what I'm saying is that you can modify A by changing the by doing transformations at the ends of every link. And of course, if you're on a closed loop, that would always drop out.
Okay. Yeah, I thought somehow the definition when you said that there's no, basically there's no continuous transformation, there's anomalies. So the idea was to define the gauge field without really defining what A is, right? So in terms of
No, it's actually useful to introduce what A is. I mean, I tried to emphasize the gauge invariant information as the cohomology class, but for many purposes, like if you want to write an action for a discrete gauge field, you may actually wish to introduce an A. Another kind of bigger point related to this comment is that one has to be careful in this discussion because, you know, we're often some of what I talked about and what we were just discussing is about anomalies. They've got kind of like subtle failures of gauge invariance. To make those kind of features of quantum field theories manifest, it's important that you explicitly use the connection. Then you check gauge invariance. It may not be actually true. Maybe it's wrong by a little bit. And that being wrong by a little bit is the kind of anomaly behavior that we found so interesting. So that's true whether you're talking about continuous gauge fields or discrete gauge fields. That in order to write explicit formulas using actions, you'll be forced to introduce connections. And then you'll sometimes find that things are not exactly gauge invariant on the nose.
So how do you know this connection? Is it a discrete or continuous gauge connection? I mean, maybe I need an example of a discrete gauge field or action.
Well, we could take G as Zn, and then we have some triangulation, and we're trying to do sort of like, singular, we're basically doing singular cohomology here in the language of algebraic topology. So we have some triangulation. And C0 of MG is an assignment of B in G to each point in the triangulation. C1 of MG would be the same thing, but now to each link. C2 MG would be the same thing to each triangle. And if I had drawn a bigger thing, C3 would be to each tetrahedron and so forth. Now, when we're talking about discrete gauge fields, we're looking for assignments of G to each link, so elements of this, which first of all are closed. That means that if I sum up the assignments going around a triangle, I get 0. And second of all, I want to mod out by those that are exact. I want to mod out by those assignments that can be generated by just taking differences of G elements assigned to each vertex, each point. So that's the closed modulo exact part that we were talking about. And so if you look into this is exactly the definition of singular cohomology. And so what we're left with here is just the holonomy of the gauge field. Now, if you try to do this for a continuous gauge field, you'll be missing something. You'll be missing the curvature. So this will give you like the right thing for flat gauge fields, but it won't tell you about gauge fields with curvature.
Okay, well, thanks. Are there any questions about this or any other part of today's lecture?
Okay, if there are no questions, then I'll tell you about something else for a little while. Okay, so maybe we can start a little ways discussing anomalies in SUN Yang-Mills. And for this, we'll have to include the theta term. So, okay. We know that there's this ZN1 symmetry. So what we'd like to know is there an anomaly in this symmetry? So what do people think? Can there be an anomaly in this symmetry? This is supposed to be a discussion. So I hope that some people will discuss. No? You should know, you actually know absolutely everything you need to know just from watching the lectures. You don't need any outside knowledge to answer the question, can there be an anomaly in this symmetry without referring to any other feature of the theory? How could we address this? How do we check whether there could be a symmetry? Whether there could be an anomaly? So. Well, okay, I'll take you some distance. So as an aside, let's remember we were thinking about anomalies. Had this kind of basic definition. Sorry, d lambda. So we thought that an anomaly was a non-zero omega that we couldn't remove no matter how hard we tried. So it's some kind of non-gauge invariance. So if omega is non-zero and non-removable, then this implies immediately that A cannot be made dynamical. Right. In this discussion of anomalies that I presented to you, I was focused on global symmetries. A was a background field for a global symmetry. And so it was not summed over. To make it dynamical, I would like to sum over it, to path integrate over it. And of course, I'd like to path integrate over connections modulo gauge. But if I find a non-zero omega, there's no way to do that integral over connections modulo gauge because the partition function z of a is not exactly gauge invariant. So hence I get this conclusion. If the anomaly is non-zero, you cannot gauge. You cannot promote A to be dynamical. Okay, so now let's come back up to this question. We're studying SUN Yang-Mills. We think maybe we'll envision in our mind there's a theta term. We're agnostic as to the value of theta right now. So there's this ZN1 one-form symmetry. And we'd like to know, can there be an anomaly in this ZN1 one-form symmetry? So now does anybody have a guess based on what I said? So the answer is no. There's an emphatic no here. So I'm coming back down. Why? What does it mean to gauge the Zn1 form symmetry? This takes us to S mod Zn gauge theory. We discussed that today. And of course, that gauge theory exists. There's nothing wrong with it. So just having that as a consistency check tells us that there couldn't have been any anomaly for this Zn1 form symmetry on its own. Now, this should jive with some lore that you perhaps know about. The lore is that SUN Yang-Mills at theta equals 0 is gapped and confining. Now, in fact, okay, so we learned a little bit about what these mean in a more modern language in these lectures. So we learned that this means that Zn one form symmetry is preserved at long distances, not spontaneously broken. Gapped, of course, we know, but actually there's a stronger claim here that's usually made in the literature. Namely, the claim is that it's trivially gapped. Remember, we'd like to distinguish field theory being gapped and being trivially gapped. Trivially gapped means the long distance is as boring as possible. There is just a single ground state, and there's no interesting correlation functions to discuss. Whereas gapped but not trivially gapped means the long distance would be some topological field theory with topological correlation functions. And so the typical lore about SUN Yang-Mills theory at theta equals 0 is not just that it is gapped, but rather that it is trivially gapped. Okay, so this is also only possible, learned, this is only mathematically consistent if there are no anomalies. So you could turn it around. If you were today to go home having heard these lectures and find a new anomaly of SUN Yang-Mills theory, you should immediately publish because you will have falsified one of the clay mathematics problems, one of these $1 million problems. So, the consistency of that problem, I remind you, is to prove rigorously that SUN Yang-Mills theory is trivially gapped. And so here we see that there's a necessary condition. The necessary condition is that there can't be any anomalies. Okay.
I'm sure you would get 1 million though.
Yeah, no, you won't. I think you won't get the 1 million. I think the phrasing of the problem is only for an affirmative answer. If you just prove that the problem is a bad problem, then I think you don't get anything. Yeah, it's like one of the Millennium problems is to prove the Riemann hypothesis. But if you falsify the Riemann hypothesis, maybe you don't get anything. Okay, questions about this? I'll keep going if there are no questions, but I'm not sure if no questions mean that nobody is even there. It's really unclear. All right, so we keep going a little bit for a few more minutes. So, okay, what we learned is that if we're just discussing Zn symmetry, there definitely can't be any anomalies. We've seen a couple pieces of evidence pointing to that. Let's now ask what's going on with other symmetries. So let's look at the theta term in more detail. So the theta term here, theta over 8 pi squared integral trace f wedge f. This is, of course, just weighting the different topological sectors in the sum over bundles with an e to the I theta. Great. So there's a symmetry at theta equals 0. This is time reversal. Or reflection symmetry. This is broken by general theta. How to see that? Well, it's useful. This is written as a nice integral of a differential form. It's useful to unpack it a little bit. So if I write this as theta, there'll be some number I won't try to get right. Integral f mu nu f rho sigma epsilon mu nu rho sigma. So how does reflection act on this? Well, reflection would flip the sign of the epsilon tensor. So reflection sends theta to minus theta. So theta equals 0 is special because it's preserved under theta to minus theta. There's a new symmetry. So we'll call that symmetry T for time reversal. And just as before, when we said we hope there's no anomaly, one can, in fact, by a nice investigation, check that there's no anomaly involving T and the one-form symmetry at theta equals 0. Okay, so what else is there to say? Well, are there any other points that have time reversal symmetry? Does anybody see the answer to that?
Theta equals pi.
Theta equals pi, great. So theta equals pi is also T invariant. Why? Well, theta is periodic with periodicity 2 pi. That's why it's called the theta angle. The reason is that 1 over 8 pi squared integral trace f f. This is what in the other lecture I called the instanton number, which is an integer. So if you are at theta equals pi, then T seems to change you. It changes you to minus pi, but minus pi and pi are equal modulo 2 pi. So theta equals pi is also T invariant. Okay, so now we have an interesting question. Can there be an anomaly involving T and the one-form symmetry at theta equals pi? We know that if we ignore T, there cannot be any anomaly. So just using the one-form symmetry on its own is not good enough because the one-form symmetry is possible for any value of theta. You can always discuss SUN mod ZN gauge theory. So the answer to this question is yes, there can be an anomaly involving T and ZN1, one-form symmetry. So in fact, there is an anomaly. at theta equals pi. Okay, I guess I don't have time to tell you how to derive that anomaly, though I think that you now have all the skills that you need to do it if you've been paying attention in these lectures. But I will say that some conclusions that can be drawn from this. So there is an anomaly at theta equals pi. So what we conclude from this is that SUN at theta equals pi is not trivially at long distances. So, you might have thought, going back to the lore that we had here, where you had SUN at theta equals 0 being gapped and confining and probably even trivially gapped, you might, if you're a naive person, have thought that, well, that statement should persist in the family as I vary theta. And what this shows is that that is not possible. At theta equals pi, something must happen. So that's our first general conclusion that we would get from this. We can say more. We can also say, now I'm just going to quote for you some results, that so this is a result of Komorgodsky, Kapustin, Gaiotto, and Seiberg. And then there's another result due to myself and Omuri, which is that SUN at theta equals pi is either, okay, one, it could be gapless. That would be interesting. Or two, gapped, but either T or ZN1 must be spontaneously broken. So it cannot, in other words, what am I ruling out here? I'm telling you it cannot be gapped, T invariant, and confining. That's impossible. So one has these two behaviors. And, you might think that being gapless would be very exotic at theta equals pi. Perhaps it's worth reminding you about the CPN model in 2 dimensions, which also has a theta angle. So the CPN model for at theta equals pi in 2 dimensions for n equals 3 and above is gapped and spontaneously breaks time reversal. But the n equals 2 and above. The CP1 model at theta equals pi is gapless. So the answer here actually is possible to depend on n, with maybe some exotic behavior at small n. And it's not really known, though it's believed that option 2 is always realized. Okay, so I leave you with this some interesting lore about Yang-Mills theory.
Any final questions? In this case, I mean, we just said that Zn1, if we just consider Zn1, that there's no anomaly at any theta, right?
By itself. What I'm saying is that there's a mixed anomaly between T and Zn1. So if you gauge Zn1, you can always do that, but it means you'll break T.
All right. Okay, thank you very much, Clay. I think we should pass to the next discussion. And thank you very much for your set of lectures and for your time discussions for preparing these lectures. I think we learned that there are many things that we do not know. And
a ringing endorsement. All right. Well, good luck learning all the things that we don't know to all of us. All right. See you.